Professor Rignot. I'm sure you'll take a few questions.
Yes.
So we have one offering.
I may have missed it, but the first time I saw any mention of carbon emissions was in your, just before your conclusions, when it says, what do we do now?
Yeah.
And it seemed to just be presented there as a cause of some kind. You didn't really build any case for carbon emissions. Can you spend some?
Well, what we're seeing in the ice sheets today is a result of climate change. And how climate change is caused, what causes climate change, ice sheets won't tell you. I mean, at least the dynamic part of the ice sheets won't tell you. If you look at the climate records in the ice sheets, they'll tell you that, carbon emissions have been increasing, and there's never been so much carbon in the atmosphere in the past several 100,000 years. So, I mean, we have to be careful about what we say from ice sheets in terms of, what causes that. I can't say what's happening in Greenland today is caused by anthropogenic climate forcing. It's caused by a warmer climate. It's caused by warmer ocean and warmer air temperatures. It's the direct consequence of climate warming.
And your hope is that the carbon emissions can be controlled. The implication is that carbon emissions are somehow causing this ice phenomenon.
Well, you can make this inference. Yes, I mean, we know that climate warming is caused by these carbon emissions. We know that. It's a scientific fact. So this is the result. And what I'm showing you today is that the future is not in 100 years, the future is now. This is affecting ice sheets today. To put it in kind of a naive perspective, I would say that the ice sheets are 100 years ahead of schedule compared to what we thought was going to happen to them. They're 100 years ahead. The things we see in Greenland and Antarctica today, if you look at these IPCC reports, they were predicted for year 2100 at the most. So what does that mean for 2100? That means we know less today than we thought we knew yesterday. But these ice sheets are going to respond in a much bigger way than what we thought. I mean, if you compare numerical models or even conceptual models, reality is going faster. This is true for ice sheets, and I think it's true for sea ice too. You see, we find the same results on the sea ice community. We have all these curves of decreasing sea ice cover in the Arctic, and observations show what goes even faster. Yes?
You have not mentioned the Arctic. And I gather the Arctic is melting even faster than Antarctica, correct?
You want to repeat the question?
Yeah. The question is about the Arctic, because I mentioned the Arctic, that the Arctic is warming faster than the Antarctic. The Arctic is melting about 2 to 3 times the global average. The Antarctic a little bit less. But for ice sheets, as I tried to say in my presentation, what's going to matter is what the ocean is going to do. The ocean can warm up, but also you can have change in ocean circulation. Change in ocean circulation are driven by atmospheric circulation, they're driven by wind patterns. So it's the whole climate system that's connected together. And what happens in Antarctic is not remote from what happens in the Arctic. This is the global climate system.
Well, I think what I'm confused about is that with the Antarctic and the ice sheets, I mean, aren't the Arctic and Iceland and all that, aren't they, do they not have the ice sheets, or why is the Antarctic so important that the Arctic was not discussed with your measurements? Is there an ice sheet differential?
Well, I talked as much about the Arctic as the Antarctic, and you have to realize that the Antarctic is in a much better setting. It's in a colder climate. It sits at the pole. Greenland is not even at the pole. Most of Greenland, above 80 degrees north, is nothing. Even above 75 degrees north, there's not much ice. So Antarctica is almost creating its own climate, sitting at South Pole, and there's this big twirl around the Antarctic that makes its own climate system. So it takes a little bit more to disturb that system. Did I answer the question? I'm not sure.
Maybe you could just say how much more ice there is in the Antarctic.
10 times more. 10 times.
The ice sheet, big ice sheet.
Yeah. The ice sheet in the Antarctic, 10 times more than 60 meters of global sea level rise versus 7 meters.
So, because from what the lesson before, it seems like, oh, if we stop carbon emission and we just fix all the atmosphere,
Yeah.
we go back, everything's slow down. Is that true?
Yeah. How about if we stop carbon emissions today? We keep it stable. Everything goes back to what it was before. Well, I wish. I wish. Well, first of all, this system have a lot of inertia. If we change something today, it's going to affect things, you know, maybe 40, 50 years down the line. Think about the Montreal Protocol to protect us from the ozone depletion in the Antarctic. When was this done? 76?
Something like that. Yeah.
76. I don't know if you follow the news to see what's happening to the ozone hole in the Antarctic. Is it back to normal? No. What year are we? 2009?
Last I checked.
Yeah. Takes a long time for the system to respond. And once it's engaged in some form of evolution, it's really hard to turn it back. So in the Antarctic, in West Antarctica, or in Greenland, you could almost say that the next 100 years are pretty much locked in. We're not really here to decide what's going to happen in the next 100 years, but we have to realize that sea level is not going to stop rising after 2100. The world doesn't end in 20. I don't think it ends in 2100.
2012. It was 2000.
There's going to be other things going on after that. Yes. Oh, very bad. Okay.
Is the water level rise at the same rate and all over the world, or it would be higher in certain parts and lower in certain parts? Sea
Okay, you
level?
have to speak up. I'm sorry.
The sea level would rise the same rate around the globe, or would be?
Okay, is the sea level rising uniformly around the whole globe? No. And there's some studies of that, and there's some recent papers which got a lot of publicity because they said, oh, it's going to be worse on the west coast of the US. Well, that's good for the public, so the editor went for that. But this was a resurrection of a study done in the 70s. I just did it a little bit better this time. But no, it's not uniform. In fact, close to the ice sheet is going down. And this, some places, you know, it's going up far faster than others. It's very highly non-uniform.
You have two temperature components in glacier speed up. This is the water and the atmospheric temperatures. You said that the water is more dominant factor in speeding up.
Yeah.
Is it possible that there is another source of warming up inside the water, inside the earth, rather than the atmospheric warming up?
What would that be?
The earth elemental?
The geothermal flux?
Yes.
I don't know, it's a question for an oceanographer. I mean, most of the change in temperature of the ocean is in the upper layers. I don't think we know very much about the bottom layers anyway.
Maybe you should check.
So look, what's happening to the ice sheets, the water column that's going to affect the ice sheets is the upper kilometer. The upper few hundred meters. I think we know that very well in the outer ocean. In the global ocean, this is the part that is well known. The abyssal depth, what's happening way down there, I don't know. You have to ask the question to an oceanographer. But it's not going to matter to the ice sheets.
Says this is a complete system, so maybe the system underneath in the abyss is somehow circulated into the upper.
Well, there are some complex changes in ocean circulation, but whether this is driving the system or not. Yes.
So you talked a little bit about the ocean ice sheet interaction being the dominant factor in the loss of mass of that structure. so there, and you say that there's a positive feedback cycle that's occurring right now that's going to accelerate that process. Can you say something about what the negative feedback cycle would be? In other words, how we're starting from point X and we're going to decrease in mass.
Yes, yes.
At some time in the past, we must have increased in mass. How does that happen?
Negative feedbacks. Well, you know, if the glacier retreats inland and then reaches higher ground and becomes grounded above sea level, it's going to slow down the retreat. It might even stabilize the glacier.
Well, how would it ever grow back into the ocean?
To grow back into the ocean, you would have to put more snowfall on the ice, and that's going to be a slow process. To reconstruct the glacier is going to take a lot more time than it took to destroy it. And that's what you see also in glacial ages. It takes a long time to build an ice sheet, and then they decay very rapidly. You know, it's a sawtooth pattern in the ice cores. It's pretty much generic of the history of the glacier. So you would have to cool down the ocean and put a lot of snow on the ice and wait a while, a long while.
Question?
Yeah, I live at 300 feet, so I'm kind of wondering what the limit is. If every scrap of ice melted, how high would the ocean go up? Do we know that number?
A meter, 3 feet by 2100. I don't know if I'll be around by 2100. You think I'm going to be around by 2100? I don't know. I remember last time I went to Baja California. The first time I went was in the 80s. And things changed a lot. You know, the Bay of Cortez, you know, this part of, which used to be a little bit wild, and the roads were kind of, you know, you could not go on a regular car on this type of roads and drive 20 miles an hour so you don't fall in the next hole. And now they have this nice highway, and a lot of people move there and build houses right at the beach, you know. And I was looking at that and thinking, geez, what's going to happen to these people? They're gonna have the ocean at their feet. Yeah. It's gonna take a while, but it's gonna come. It's just a matter of time. It's gonna come.
Was there a
But 100 feet, unless you live another 100 years or so, I think you're fine.
Point in past history where, in fact, there was no ice?
I'm sorry?
Was there a point in history where there was no ice?
Oh, yes, yes. Yes, a few million years ago. Yes.
It's the time when the ocean was boiling, right?
Yes. Oh, yeah. All the Earth went through all kinds of things.
All right, one more question.
Would you care to guess how long it would be before the North Pole is ice free?
Oh, North Pole ice free. That's a sea ice question, huh? I remember when Al Gore came to the fall meeting at AGU in San Francisco and made this speech about global warming and all that stuff. There was a word that the sea ice cover would be gone in the summer by 2040. A year later, well, this was kind of outrageous at the time. It was like, who published that? Is it published? A year later, people were saying, it's probably going to be 2020. I think right now people even propose that there's going to be no Arctic sea ice cover in 2013. So it's going fast.
But that doesn't affect ocean level.
But that doesn't affect ocean level, and it doesn't affect sea level rise. And I'm sorry guys, sea ice is not, I mean, ice sheets are far more important.
I want to thank Professor Rignot for a fascinating. So if you want to ask some private questions, he's willing to stick around. Let me advertise, please, our next physical science breakfast on May 19th. This is going to be a very special edition of the Physical Science Breakfast because our beloved ex-dean and chancellor Ralph Cicerone and his wife Carol will be visiting and attending. They're endowing a new graduate fellowship in the School of Earth System Science. And the speaker will be one of our popular physics professors who even speaks on TV about
The Science of Superheroes. So I highly recommend that as the next edition in what I think has been an extraordinary year of good physical science. One request, physical sciences runs a tight ship, so please leave your name tag on the table so we can save a few dollars and keep this whole thing going. And thank you for attending.
He dismissed the
Have a great
question
day.
about other sources. As the top layer, what happens down below doesn't make that much difference.